Alright, so picking up from our last video, we're looking at example 4, which is going to be this supersonic man problem. So on October 14th, 1947, Chuck Yeager flew his X-1 rocket plane at an altitude of 12.8 kilometers. He was clocked at 299.5 meters per second, which is about 669.962 miles per hour. At different altitudes, sound travels at different speeds. We can model this variation for speed of sound with a piecewise function defined given below. In part A, we're going to integrate the function over the interval from 0 to 80 for 5 subintervals. So what we're going to do for part A, I'm going to use this space off to the side, is we're going to look at the first integral from 0 to 11.5 of that first part of the piecewise function. So negative 4x plus 341 with respect to x. And I'm going to just use my calculator to do that. When I do that, I get a value of 3,657. But that's not the only part of the function. So I'm going to do that for each part of our function. I'm going to take from 11.5 to 22 of 295 with respect to x. Again, I'm just going to use my calculator. I could do this one by hand, but there's a lot of them we're going to do. I'm just going by calculator. That's going to give me 3,097.5. And then we're going to do this for all the parts. We're going to take the interval we're given for each function and just integrate on that. So we're going to have 22 to 32 of 0.75x plus 278.5 with respect to x. In my calculator, when I put that in, I get about, now this one has a decimal, so I round it to 2,987.5. I'm going to just keep going from 32 to 50 of 1.5x plus 254.5 with respect to x. I'm going to get the value 5,688. And then lastly, I'm integrating from 50 to 80 of negative 1.5x plus 404.5 with respect to x. And I get 9,210. So that's all we had to do for part A. For part B, we're going to apply the mean value theorem for integrals to find an average speed of sound. So all we're going to really do for part B is we're going to take the integral from 0 to 80 of our s function, which we just found a bunch of values for that with respect to t, over 80 minus 0. So what I'm going to do is I'm just going to take those values that we just calculated in part A, the 3,657 all the way to the 9,210, and I'm just going to add them together. And then we're going to divide them by 80 minus 0, which is just 80. When we do that, now I've run out of space, so let me clear off this stuff from part A. Using my calculator, I'm going to find that this is about 308 meters per second. So then to do part C, we're going to graph that. Now, we're just going to approximate the graphing part. We know 308 is going to be between 300 and 310. So we're just going to take our graph and draw a horizontal line where we think 308 is. And write y equals 308. And that's the end of example 4. So now we're also going to look at the net change theorem. The net change theorem says that the definite integral of the rate of change of a quantity gives the total change, or the net change, in that quantity on the interval. In fact, it looks very similar to the fundamental theorem of calculus. So all it really is that we're looking at displacement from A to B is going to be the integral from A to B of the function, where we add all the little bits under the curve. And if it's below the x-axis, then we subtract them. And then the total distance traveled would just be adding up all of those values. They'd be finding the absolute value of that function. So now moving into our last example, example 5, we have a particle moving along a line so that its velocity is represented by the function t cubed minus 9t squared plus 15t plus 10 feet per second at time t. We're asked in part A to find the displacement of the particle from 0 to 5. So we're going to be looking for the integral from 0 to 5 of vt with respect to t. So we're going to look and integrate the function we were given. So we're going to have t to the 4th over 4 minus, if we raise the power by 1, we're going to have t cubed. And if we divide 9 by 3, we'll end up with just a 3. Plus, we increase t there. 15 divided by 2, let's just write it as 15t squared over 2 plus 10t from 0 to 5. So now let's evaluate. We're going to have 5 to the 4th over 4 minus 3 times 5 cubed plus 15 times 5 squared over 2 plus 10 times 5. So that's going to give us 625 over 4 plus 375 plus 375 over 2 plus 50. Now, I'm totally cool with you writing these as decimals, so let's just do that. 625 over 4, that's 156.25 plus 375 plus, in fact, I made one mistake in my work here. Before I move on, I need to fix that. I should not have written a plus 375. These should be minus 375s. Plus, now I can go back. 375 divided by 2 is 187.5 plus 50. And now I'm just going to use my calculator to find what that value is. It's going to be 18.75 feet. So the displacement is just 18.75 feet. Now we're going to find the total distance. Now to find the total distance, we're going to take the integral from 0 to 5 of the absolute value of the function with respect to t. There is a way for us to put this into our calculator. I'll show you how to do this in class. But when we do that, we're going to get that the value is about 54.833 feet. And that actually wraps up our lesson on the mean value theorem for integrals.